In this video, you'll learn two different methods for corner detection using OpenCV for Python. This is video 5 of a tutorial series all about OpenCV for Python. We've learned things going back to the installation, some history, and then also the basics, working our way up to more complicated things like drawing, image manipulation, and most recently in video 4, it was webcams and video. Right now we're doing corner detection, and we're going to work our way to more complicated things like facial detection in the next video. Before we talk anymore, let's get into our preferred IDE. I'm here in Visual Studio Code. All this code is on GitHub. I have the page linked in the description, and I also have a playlist to all of these linked in the description. Let's start out with the basic import CV2, and then we're just going to read in an image. But because we're doing corner detection, we're not going to work with the normal image, Ella, that we've gotten so familiar with. I made a new image in MS Paint called shapes.png. It's in the GitHub if you want to use it, in my assets folder. And we're going to find all of these corners by the end of this video. What are the first steps? You've probably become familiar with this now. Image equals cv2.imread. We're reading in the image. Assets, and then what did I call that? Shapes.png. Okay, and let's just show the image so we know we're doing everything correctly. cv2.im, not read, show. What are we calling this image? This window, we're going to call it shape. We're going to show image. cv2.waitKey 0. Just pause the program until I press a key on the keyboard. And then once I do press a key, we're going to destroy all windows. You've seen me write this 5 times now, and hopefully you're getting the hang of things. Let's run that. And there we go. There's my shape. Window's called shape up there, pretty tiny. Press any key, it gets destroyed. For corner detection, it doesn't really care about color, so let's convert everything. I'm going to call this gray image equals cv2.convert color. We're converting everything to grayscale. It's just simpler to work with for corner detection. What are we converting? Our image. And then how are we converting it? We're going to go cv2 color underscore. Let me close this so it's bigger. Currently it's in BGR form, and we're going to gray. Next. The first method I'm going to show you is called the Tomasi method. And how this method works, let me pull up a whiteboard. I have my whiteboard up, and how this method works, let's take our shape. We have a random trapezoid. We want to just assume this is a normal corner. We want to look for all the corners on there. Obviously, we can see this is a corner, this is a corner, this is a corner, and this is a corner. But how can a program figure that out? What the Tomasi method does is it has a little box, sliding window, and it slides around and looks at everything. When it's here, it's going to see that there's a line, and the line enters here, and it's going to do some translation. It's like, if it enters here at this angle, it's going to exit here at this angle, as predicted. It can tell that there's no corner there because it's as predicted. But now, say we move over here, where is it going to predict? Say it sees this coming in at this angle. It's going to go, and say, oh, I expect it to go out here. Instead, what we see is it actually comes out at this point. That's a large difference. And based on that size of the difference is the quality of the corner. What it does is it takes the highest quality corner, the biggest difference, and then takes the next X corners beyond that. Okay, let's execute this. Corners equals CV2 dot good features to track. You may think that's an odd name for this, but why isn't it just called Shi Tomasi? The paper that Shi and Tomasi wrote is called Good Features to Track. It also has like 11,000 citations, so it's pretty popular. We're going to be looking at image. Actually, no, we're not. We're looking at gray image. And then what were the other things that I said were important? Quality level, so how the quality of the corner, the max number of corners we're looking at, and then there are a few other parameters. Max corners, quality level, min distance between each corner. This corners is an output vector. We're not going to use that. And then we'll get to the other things later. So, max, what was it, underscore? No underscore, camel case. Max corners, let's just look for 50 total corners. There are definitely not 50 corners in my image, but I'll use this to show something. Quality level equals 0.1. We're going to mess with this parameter. And then finally, min distance between corners, let's say 50 pixels. I would like to throw these corners onto my image so we can see where it's actually detecting them. Notice I'm showing the image here. I'm going to keep that. So for C in corners, it's just a list of XY coordinates. X, Y equals C dot ravel. Now we're going to draw a circle for each of those points. Image equals CV2 dot circle. This is from video 3. What do we have? We're going to draw on image. Center equals X, Y. Radius equals, I don't know, 20. We're going to make big circles. Color equals, let's make it red. And then finally, thickness equals -1. We want these circles to be filled in. Okay, let's run that, see how it works. And we have an error. What's the error here? I forgot to cast corners to integers. Right now it's some kind of float probably, so numpy.int 0 corners, we're going to cast everything to be a numpy.integer format. And then we also have to import numpy as np. Okay, run that. And we have another error. Oh. It's the same error, but I still have corners and I forgot the S. Classic syntax. Boom. Oh my goodness, that's a lot of corners. But it's as we'd expect because we're going to get better and better. This is just the most basic method. The thing I'm noting here is there are corners on the circle. And if I remember correctly, circles either have infinite corners or no corners. I'm going to say infinite. But for the purpose of this detector, we'd like it to detect no corners. These three shapes are great, but then there's some random ones here. There's jagged pixels within my corner detector. Like in this image, I just drew it in MS Paint, so you can barely see the jagged pixels of it. But we want to ignore all that and detect proper full corners, how we understand them. What we can do is we can start tweaking quality level. So let's require quality to be 2 in the corners. Run that, and we get it to be way better, but we miss one on the triangle. So we're going to drop quality level down to be 1.5. Yeah, it's tough. So this one detects way more corners than we need. We can increase max distance to be 100, but that's still not perfect because then we miss some on the star. What's the solution here? The solution is to try a different detection method. We're actually just going to copy all of this. Paste it here. And now we're doing the Harris corner detection, named after another paper written by Harris and then another person, I don't remember. It's more complicated than the Shi-Tomasi and works a little better. Essentially, where the Shi-Tomasi is just in doing that simple interpolation, the Harris corner detection looks for a variance in the direction over all directions. It's a bit more comprehensive from how I understand it, but also I'm just a layperson here. I'm sure somebody in the comments can come up with a better explanation. We want to use the Harris corner detection, so we're going to do, I believe it's Harris something. Use Harris detector. True. And then that takes this parameter K. I'm going to set that to 0.1. Now we have corners. We're going to draw them again, but I'm going to keep the corners from the Shi-Tomasi so we can see and compare. But now let's make them 10, and rather than drawing them in red, let's draw them in green. Alright, run that. Look at that. So we have all our red ones that are just way too many, and now green, which is just missing the ones on the triangle, but it's got every other corner perfectly. So we can tweak our parameters and hopefully get there. Let's dive into this K parameter. Some more details on how the Harris corner detection works is it looks at two different gradients that are incoming. So if we have a line coming this way and a line coming this way, that's going to be two gradients that hit each other. How far off do the eigenvectors, we're getting into some linear algebra here, have to be? How far off do they have to be for it to be a corner versus not a corner? How far do these eigenvalues of gradients need to be? That's the K value. Higher K means fewer false corners, as we see in the circle, all these false corners, and in that rhombus. But it looks like we're neglecting some of the corners in the triangle. We're going to lower quality all the way down to 1/100th. K is at 0.1. I also noticed a typo. Destroy all windows. Dostoevsky. Okay, let's run that, check it out. And we have every corner nicely detected. Press a key to close out. Now there's no error after destroy all windows. Just for posterity, I'm going to save this image. cv2.imWrite, file path, assets. This is video 5, shape with corners.png. We're going to save our image. Run that, close it. We see 5, shape with corners, and there's our output. Green is the Harris, red is the Shi-Tomasi, and that's it. That's two straightforward corner detection methods built into OpenCV. There are way more if you want to get into it, but this should be a good starting point for you in corner detection. If you're following along with the tutorial series, maybe you're in the playlist, you can go forward to video 6, and that's going to be facial recognition. We're going to be looking at the smile, eyes, and face for detection. As always, if you have any comments, leave them in the comments section. I try to get back to as many as I can. Leave a like if this was helpful, and subscribe so you can watch more of my videos in the future. I'll see you in tutorial 6, and happy coding.